The state of the environment is drawing increasing concern worldwide. Humanity's use of carbon-based fuels is unsustainable, and around the world, governments are beginning to take action to mitigate some of the negative impact we have had on our planet. As part of second-year studies in aeronautics at Imperial College, London, students are required to design and build a wind turbine. This links our studies of aerodynamics, aircraft structures, and manufacturing methods to an important consideration for the future of human existence. We are Student Group 4, and this video is a summary of our design process. To begin with, we were given a number of design constraints. The turbine had to feature two blades and had to rotate clockwise when viewed from the wind direction. It was not to exceed 3,000 revolutions per minute at a maximum wind speed of 12 meters per second. The turbine was required to self-start before the wind speed reached 10 meters per second. The turbine needed to be no more than 400 millimeters in diameter and have a total weight less than 400 grams. The blade needed to be optimized for best performance at a tip rotational velocity of 3 to 8 times the incident wind speed. This number is known as the tip speed ratio, or TSR. Additionally, we were told that creativity would be considered favorably as part of our assessment. Given these constraints, we aim to achieve a rotational velocity of exactly 3,000 RPM with a 12 meter per second wind speed. We decided not to worry about the self-start parameter, since if our turbine hadn't started rotating by the given wind speed, we would be unlikely to reach our target RPM. We chose to make our turbine as big as we could possibly make it, hoping that a conservative blade design wouldn't exceed 400 grams in weight. Our target tip speed ratio was 4. This was chosen because we had observed that previous wind turbine experiments using similar design parameters typically exceeded their target TSR, and aiming for a larger value of TSR, such as 5, might lead to the turbine exceeding the RPM limit, which occurs at a TSR of 5.37 for our blade diameter and a 12 meter per second wind speed. Generally speaking, we decided that taking a simpler, more traditional approach to design, whilst potentially detrimental to the creative aspect of the project, would generate better performance results. We are prospective engineers after all. With our targets and design philosophy set, 4 tasks remained. 1. To actually design the turbine. 2. To manufacture it. 3. To test it. And 4. To evaluate its performance.
In designing the turbine blade, we first needed to consider some turbine blade physics. In brief, turbine blades perform better with greater surface areas and greater incident airspeed. The angle the blade makes with the incoming wind is called the angle of attack. The performance of a given cross-sectional blade profile, or aerofoil section, depends on the angle of attack. Different aerofoils also perform differently at a given airspeed. Because it's rotating, the tip of a turbine blade has a higher rotational velocity than at the root. This means less surface area is required for the blade to perform well at the tip. The blade can therefore be tapered, minimizing the force required to make it rotate. The higher rotational velocity of the tip also has the effect of changing the angle of incident airflow when viewed from the side. To make the blade perform best, it needs to be twisted to achieve the optimum angle of attack at every point along the blade radius. In summary, these were the questions we had to answer. 1. What aerofoil sections will we use? 2. How much can we taper the blade? And 3. How much do we need to twist the blade? To answer question 1 on the aerofoil sections, we hit the books. Our research indicated that both the SG6042 and E61 aerofoils would perform well for our design parameters. The E61 aerofoil is better for high-speed applications, and since it is a much thinner profile, it was a logical decision to use this profile closer to the blade tips, where the structural stresses are lower and the rotational velocity is greater. We used the SG6042 aerofoil section closer to the blade root in order to optimize performance. To get an idea of how these aerofoils would perform during testing, we used the turbine simulation software QBlade. Whilst overly simplistic, QBlade essentially provided us with a proof of concept indicating that our turbine was likely to perform as expected. It also gave us an indication of the regions in which we could use our chosen aerofoil sections for good performance, as well as how much blade taper and twist we might use. However, more detailed calculations were still needed to determine these parameters exactly. The Smiths and Betts formulae are well-known tools for determining blade twist angle and taper given the radius and the desired angle of attack. We used the program MATLAB to give us results for both of these equations given our design decisions so far, hence answering both questions 2 and 3.
Additionally, we needed to consider the structural integrity of the turbine blade during testing. Specifically, we were interested in the maximum tip deflection and critical stress in the blade, which were constrained by the properties of the construction material, which was an ABS plastic with a yield strength of 21.6 megapascals and a Young's modulus of 1.64 gigapascals. To determine the values of these parameters, we modeled the blade as a simplified beam and used MATLAB to perform the calculations. This analysis enabled us to conclude that the blade wouldn't fail under the loading likely to be experienced during testing. The part joining the 2 turbine blades, called the hub, also requires some design considerations. We determined that this element of the design wasn't likely to impact performance greatly, and so we opted to keep it simple as possible, choosing a depth of 55mm and a diameter of 40mm, in order to accommodate a 16mm diameter mounting shaft securely. In order to minimize weight, we decided to drill holes through the aluminium component joining the blade structure to the shaft. With all of our numbers worked out, it was time to begin drawing. We used the computer-aided design program Creo to generate our model. While simple to explain and pretty to look at, this was certainly the most time-consuming part of the design process.
The manufacturing process was completed in 3 parts. Firstly, the entire blade, including the hub, was 3D printed. While simple in principle, the printing direction is an important consideration since different directions have an effect on the surface finish and structural integrity of the blade, especially at its thinnest regions. This led to our design being printed 3 times in order to ascertain the best printing format. The second part of the manufacturing process was the machining of the aluminum section of the hub. This was done by firstly using a lathe to achieve the desired thickness in a cylindrical profile and to drill the central hole used to mount the blade to the testing apparatus. The next step was to mill the cylinder into a hexagonal cross-section and drill a series of holes in the flat faces in order to reduce its weight. We then used the lathe to remove the excess material used during processing and broach the keyway into the central hole. The final step was to stamp our group number into the part. After assembling the printed blade and aluminum hub attachment, the final part of the manufacturing process was to improve the surface finish by hand sanding the blade using a series of increasingly finer grit sandpapers. There was a small inconsistency on the surface of one of the blade tips, and we mitigated this by applying some clear lacquer to the defect and then sanding it back to match the intended blade profile. Our blade was now ready for testing.
Unfortunately, during testing, our turbine blade did not self-start, despite running the wind tunnel up to and above the maximum testing wind speed of 12 meters per second. Ultimately, the turbine was started by nudging one of the blade tips. Once the blade was spinning consistently, the wind tunnel was set to the testing wind speeds of 12, 10, 8, and 6 meters per second. During each of the tests, the rotational resistance was first increased and then decreased gradually to determine how effective the blade was at generating power. At 12, 10, and 8 meters per second, the turbine was capable of generating power. However, the turbine stalled at a wind speed of 6.5 meters per second. During the 12 and 10 meters per second tests, it was observed that the turbine experienced some resonance around 2,750 revolutions per minute. During the 12 meter per second test, this rotational velocity corresponded to the maximum pressure coefficient of the turbine, which is not ideal. This resonance could not be observed during the 8 meter per second test, since the turbine did not reach 2,750 RPM. Additionally, it was determined that the tip speed ratio of the turbine at a 12 meter per second wind speed was 4.5. This was consistent with our design assumptions, as it was slightly higher than the design target TSR of 4.
The most significant conclusion to be drawn from our test results was that, for its weight, the power generated by a turbine was mediocre when compared to other group designs with the same constraints. This is evident from our value of maximum power coefficient, or CP, which was 0.163. Additionally, like us, all of the other groups failed to self-start. This is likely due to a continued reduction in turbine diameter from previous years, whilst utilizing the same testing equipment. The result is too great an inertia for the turbine to overcome, while still generating power efficiently. A possible way to self-start would be to essentially make the blades into O's and turn them to catch the oncoming wind. However, such a turbine would be very inefficient in generating power. Thus, we can conclude that we would need to twist the root of the blades to a higher degree if we wanted the turbine to perform better, given the same constraints and the self-start. Our structural analysis showed that the root of the blade was only subjected to 22.7% of the yield stress, and the tip deflection was small, which was backed up by the test results. Hence, we concluded that our safety margin was excessive, and therefore could be reduced without jeopardizing the structural integrity of the turbine. This would allow us to remove mass in a new version of the turbine by hollowing out the structure and using a honeycomb for strength. The final change would be the sole use of the E61 profile, as the SG6042 was not needed for structural integrity. Apart from another reduction in mass, this change would hopefully result in a higher power generation due to the superior aerodynamic performance of the E61 profile, as seen on the CL/CD plots. It was apparent from our results that the maximum power at the operational wind speed was generated close to the resonant frequency. Considering the changes we would make to a new turbine, the resonant frequency would probably differ. Hopefully, it would also differ from the angular velocity of the maximum power generated. To ensure this, we would calculate the expected resonant frequency of the new design.